So to wrap up our proof by contradiction examples, I want to look at this problem number 1 here, which is the statement that if x is a natural number, then 5 divides into x evenly, so 5 divides x, if and only if 5 divides into x squared evenly. So let's look at a strategy for proving this statement. And because it is a biconditional statement, it's an if and only if, that means that we actually end up having 2 things that we have to prove here. So remember, every if and only if statement gives us 2 things to do. We have to prove both the if implication, so the implication going, the only if implication would be the one going from left to right on your screen. 5 divides x only if 5 divides x squared. And then we also have to prove the if implication, that if 5 divides x squared, then 5 divides x. So anytime you have an if and only if that you need to prove, it's worth putting both of those conditionals down in a separate spot. So I'm actually going to use 2 separate napkins here to organize our scratch work. Because very often, and I think we'll see that example here, the strategy that you use to prove one of these directions is not necessarily the same strategy that you'll use to prove it the other way. In particular, a lot of times where indirect proofs, so proofs by contradiction, proofs by contrapositive, where those proofs come in, is often they end up being the best way to prove the reverse implication of something whose forward implication you can prove directly. And this is one of those kinds of examples. So let's start by tackling this forward implication. If I know that x is a multiple of 5, how do I prove that x squared must also be a multiple of 5? And so we can kind of think just sort of heuristically about this, right? If x has a 5 in it, and then I multiply x by itself, does that product have to have a 5 in it? Well, sure it does, because the original x had a 5 in it, right? That's kind of the back of the envelope way to think about this. But if we want to formalize that into a direct proof, let's try the direct approach first. I think that's very often the advice that I like to give is before you jump directly for contradiction, because it's a very tempting way. Once you learn contradiction, you want to use it for everything, but it's not always the most elegant. So we'll try a direct proof first. So if we know that x is a multiple of 5, that means x is equal to 5 times some integer. I'm just going to call that integer a. I'm on my napkin, so I'm just going to remember that a is an integer right now. And then ask, well, if I know that x is equal to 5 times a, what do I know about x squared? So I'll take 5a, square it, expand out that square, I get 25a squared. And then what is important to know about x squared in order to make the conclusion we're trying to make is that we need to prove that x squared is also a multiple of 5. So we need to see x squared as 5 times something, right? And so all we have to do is ask, is 25a squared guaranteed to be 5 times something? And the answer is yes, because 25 itself happens to be 5 times something, and because multiplication is an associative operation, we can factor out the 5 from the 25 and say 25a squared is 5 times 5a squared. And if this 5a squared can fill in this blank here, then it would show that x squared is also a multiple of 5, which is what we were trying to prove. Right? So I've done a lot of work on this napkin, and these little arrows here are doing a lot of logical work that when it comes time to actually formalize and write up this proof, we have to kind of explain what our thinking is, what the thought process involved in each of these arrows is. But it would appear to me, based on this napkin scratches, that we have a valid argument for why if x is a multiple of 5, then x squared will also be a multiple of 5. And that proves what we call the forward direction. That if 5 divides x, then 5 divides x squared. So we did that way directly. What about the other way? So I want to talk first about why we might stumble if we try to do this proof directly. If we try to assume that 5 divides into x squared, what that gives me, right, is that x squared is equal to 5 times some integer. The problem comes in then trying to use that observation to infer something about x instead of about x squared. Because we're trying to get to here. But in order to do that, I would have to do something invasive. I don't know what the right word is here. Something messy. And that messy thing I would have to do is I would probably do something like try to take a square root of this equation on both sides. But then if I take a square root on both sides, I'm going to end up with a square root of 5n on the other side, and I don't know anymore what's an integer and what's not an integer, and that's going to be a problem for us, right? Because ultimately, if we're trying to conclude that x is a multiple of 5, we need to show x is equal to 5 times an integer, and it's not clear to me from this expression why the square root of 5 times n should be 5 times an integer. I don't see any integers necessarily popping out of this right-hand side. So trying to do this directly feels to me like a dead end. And that tends to be, in my own practice, when I try flipping the script and try an indirect approach instead. So in an indirect approach, what I would do is I would try to deny the consequent, take the conclusion and flip it on its head. Instead of making an assumption that 5 divides x squared, we make an assumption that 5 does not divide x. So we take and we write down not q, and we use this as the thing we're going to assume, and then try to deduce a denial of the antecedent. In other words, try to deduce that the premise is not true. If I know that 5 does not divide into x evenly, can I conclude that 5 cannot divide into x squared evenly? And this feels like something that's more manageable because our assumption is now an assumption about x instead of an assumption about x squared, which means I hopefully will be able to get from here to there without doing something as nasty and potentially integer violating as taking a square root. Instead, I'm probably just going to have to square something. And when I square something, multiply it by itself, if I start out with integers, I know I'm going to end up with integers. And that feels like the kind of thing that we want. But the degree of difficulty, and this is why your professor was sort of priming you with thinking along these ways a couple of classes ago, is that the assumption that 5 does not divide x, that x is not a multiple of 5, is one that actually breaks out into a variety of different cases that we can study. In particular, it breaks out into 4 different cases. If x is not a multiple of 5, then it's either 1 more than a multiple of 5, or it's 2 more than a multiple of 5, or it's 3 more than a multiple of 5, or it's 4 more than a multiple of 5. So there's all these different possibilities for what x could satisfy if we know that it's not a multiple of 5. The one thing that we know it cannot be is 0 more than a multiple of 5, 5k plus 0, right? But so what we're saying is that if I divide x by 5, the remainder is going to be 1, or it's going to be 2, or it's going to be 3, or it's going to be 4, but it cannot be 0, is what we're saying here. And so now this ends up in proof by cases land. In each one of these cases, can we show that x squared is not a multiple of 5? Now that we have an understanding of what the x's are, we'll just try squaring them and see what comes out. In each of these cases, x squared is some polynomial expression involving k, right? And in each case, the highest order term is 25k squared, or l squared, or m squared, or n squared, whatever we're using for that integer. 25 times an integer squared. And then it's plus some integer times k. And notice that those integers that we have in front of the linear terms here are all multiples of 5, which is kind of nice. In fact, they're multiples of 10. And then we have these constants at the end. And the constants at the end end up being the perfect squares, 1, 4, 9, and 16. So the question is, what will I get when I divide these expressions by 5? If it's possible for me to get a remainder of 0, then we're going to be stuck, right? Because we're trying to show that these things are not multiples of 5. So what we'd like is to show that when we divide them by 5, we get a remainder which is not 0, a remainder which is 1, 2, 3, or 4, namely. So to do that, we're just going to try to factor 5 out of as much of this expression as we can, leaving only a constant between 1 and 4, hopefully, as the leftovers. So if I look at these two terms, 25k squared and 10k, I notice that both of those are in fact multiples of 5, and that this 1 is the only leftover out in the front. So this x squared is already 5 times something plus 1, right? And the same thing happens if I go across. 25l squared plus 20l is also a multiple of 5, and the leftover amount is 4. In these examples, we had a constant which was bigger than 5. We had a 9, and we had a 16. And so what I'll do is I'll just break off a certain number of multiples of 5, enough to make it so that my leftover constant is between 0 and 4. Right? And so if I did it with 9, I break 9 into 5 and 4, and then I notice that 5 is a factor of all 3 of these terms. So it's 5 times an integer plus 4. And then here x squared is 5 times an integer plus 1. Again, all this stuff is happening on my napkin, so I don't feel the need on my chicken scratches to be specific about what are those integers and how do we know that they're integers. But I've done enough work on this back of this napkin to convince myself that in each one of these 4 cases, if x was not a multiple of 5, then x squared will have either a remainder of 1 or a remainder of 4 when it's divided by 5, because it's equal to 5 times an integer plus 1 or 5 times an integer plus 4. And so in every one of those cases, we can conclude that x squared is not, in fact, a multiple of 5. And that gives us then the proof of the contrapositive of this statement. Right? We've proven that if 5 divides into x squared, then 5 divides x. Because we've proven that if 5 does not divide x, then 5 cannot divide x squared. So we've proven the contrapositive of this statement. Another way to think about it, and we've been talking about this for a couple classes in a row, is we could also think of it as a proof by contradiction. In a proof by contradiction, we would assume at the beginning not only that 5 doesn't divide x, but we would assume that 5 does divide x squared. And then the work that we do here concludes that in fact 5 does not divide x squared, which contradicts our previous assumption. So whichever way that you look at it, I think the contrapositive is a little bit cleaner because we made one fewer assumption. But either way, we have proven that implication. And now we've proven both directions, and so this if and only if statement has been proven.